Here's a rather unusual fluid mechanics problem, which uses the idea of hydrostatics and the idea of that Archimedes principle and sheds a different light on it. And let's see what I mean by that. Now, if you'd like to see anything similar to this on the channel, let me know in the comments. So, we're dealing with an object which is sitting on the bottom of a tank, and we know a couple of things. So we know the fact that this object has a volume of 0.5 meters cubed, and we know the density, and we know it's glued to the bottom of the vessel. Okay, now the base of the object is flat, and that flat area has, or that flat surface has an area of 100 centimeters squared. We know the density of the water, and we also know that the glue can withstand a maximum force, which is 2000 newtons. And the question is, to what maximum height above the base, so in basically we just have to find this. Right, so we have to find this water depth. So to what maximum height above the base can water be filled so that the object is not torn apart from the base? And we have four options. We have 5 meters, 10 meters, and then we have up to any height, and then these insufficient information. So I think this kind of question is quite tricky because you don't even know if you can find the answer to begin with. In which case it would be option D, but then option C is quite tricky because it basically says that the height is completely irrelevant, and maybe you're not sure whether that's the case. But if all four options were like 5 meters, 10 meters, and then 7 meters, and maybe 15 meters, then you know that there is an answer and it's one of them. But in this case, even if you're dealing with four options, it's much trickier because you don't know if you can find the correct answer to begin with. So let's try to analyze this step by step. Now, in terms of that buoyancy theory, so if you have an object which is submerged, right, then what happens is you've got pressure acting all around it. So you've got a smaller pressure on top, and then this pressure is slowly increasing until it reaches a maximum value wherever the deepest part of the object is, and then it goes back to the top, something like that. And this pressure distribution is what creates that buoyancy force. Let's call this FB. And we know that this is actually equal to the density of the water multiplied by G multiplied by the volume of the object that's submerged. Okay, so whatever volume the object has, that's the volume that you would put in this formula. Right, now in this case, this formula doesn't really work because the object is submerged, but there is a part of it somewhere near the bottom or right on the bottom where this pressure that's pushing mostly upwards doesn't really exist because the object is stuck to the bottom of the tank. So if we draw that object more accurately, so it's got a flat bottom surface, and then it has that irregular shape, and it has a volume that we know, which is 0.5 centimeters cubed. So if this object was, let's say, at the halfway point, maybe this object would have been somewhere here like this, then there would have been pressure acting on the bottom surface, pushing it upwards. But right now, this pressure is missing because there's essentially no water underneath the object, which means that the buoyancy force is less than this value because it's missing this component here. And this component is, we can actually find what this is. That's the pressure times the area, right? So we know the bottom area of 100 centimeters squared, or let's actually convert that to meters squared. So that's gonna be 0.01 meters squared. So that's how much force, that's how much buoyant force is missing in our case, which means that when we have the object stuck to the bottom, the actual FB or FB prime, let's call it, is going to be this as if the total pressure field was acting, and that's rho WGV. But now we don't actually have that pressure acting at the bottom, so we have to subtract pressure times area. So that's actually the buoyant force acting on the object in our case. Okay, so we've got FB prime is equal to the water density times G times V minus pressure times area. So just to quickly recap, the force that the object experiences due to the pressure is this, but from that you have to subtract the non-existing pressure times area, which is acting on the bottom, and this would have existed if the object was floating above, anywhere above the bottom of the floor. Okay, so hopefully, if that's clear, we can actually move on. Now, the pressure, this is easy to find. It's the hydrostatic pressure acting at the bottom of the tank, which is just rho GH. So this is rho of the water, G times H. H is what we don't know, and H is what the question is asking us about. Okay, so we'll treat it as an unknown for now. So let's rewrite this again. So FB prime is the water density times GV minus the water density times GH times A. So we can factorize things to make the equation more a bit more tidy. So that's going to be V minus H multiplied by A. Right. So we did what I consider to be the harder part of the question, which is figuring out what this buoyant force is. Now, the other thing is, how do we exactly deal with this 2000 Newton force, which is the force that the glue can withstand? And to do that, we're gonna try to draw a free body diagram, and we'll do that here. So let's actually draw the object itself, and then we'll draw all the forces that are acting on the object. So here's what we have. We have the weight. Let's actually use some colors. So we have the weight of the object, which is mg. We have the buoyant force from earlier. Remember, this is FB prime. And also we have the glue. So what's the glue trying to do? The glue is trying to, if the object is trying to escape by going up, the glue will try to bring it back down. So that's the force, that's the glue force, let's call it, right? We can label it whatever we want. So what we then try to do is we try to find this H. So we're trying to find H such that the glue force becomes equal to 2000 Newtons. So if this object is, if there's no water in the tank, then the glue force will not really do anything. But the more this force increases, the higher the glue force will become. And the limit, the limiting value of this glue force is 2000 Newtons. So whenever this force reaches 2000 Newtons, that's the scenario we're interested in, and that's the height at which the object can actually detach and break the glue from the bottom of the tank. So let's write the balance of forces in this case. So we've got FB prime, we've got minus mg and minus F glue. This equals to 0. Okay, and then this becomes FB prime is going to be equal to mg plus F glue. And all we have to do now is just replace FB prime with this. So that's going to be the water density times G, and then we've got this bracket, which is the volume minus HA. And the mass of the object is what we need here. So mg is, well, it's the density, so that's 500. Let's actually use symbols for now. So we have the density of the object times the volume times G, and then plus the force due to the glue. And this is actually easy to do, right? This is just one equation with one unknown. The only thing we don't know is H. So we technically have to rearrange and find what H is. So let's see how we do that. If I take this term and if I move it to the right, I'll get on the right just this. And on the left hand side, I should have this minus rho 0 Vg and then minus F glue. So this can also be written as the density of the water minus density of the object times GV minus the force of the glue. And then we have, this is density of the water, GHA. Right, so we're trying to find H. And to do that, we're going to divide everything by rho W GA. So that's the stuff that H is multiplied with. And what we then get is our answer, hopefully. So that's rho W minus rho object times V over rho water times A. So basically when I divided, this G and this G canceled out. And this is going to be minus F glue divided by rho water GA. So literally the only thing left to do here is just to put in the values that we have. So let's bring this over first. And here it is, 1000 minus the density of the object, which is 500. And this is multiplied by the volume of the object, which is 0.5 meters cubed. Like that, and that's going to be divided by 1000 multiplied by the area, which is 0.01, right? And then we substitute the second term, so that's 2000 newtons, the force of the glue, and then 1000 times, let's use 10 for G, and then for A we have 0.01. It's a bit cramped, but hopefully you get the idea. So we have 1000 minus 500, which is 500 times 0.5. So let's actually replace this with 250. This is divided by, so 1000 multiplied by 0.01, this is going to be 10, minus, and this is 2000 over, so this is 10 and this is 0.01. So this is going to be 0.1 multiplied by 1000 is going to be 100. So we have 25 minus, we can cancel out 2 zeros, and we have 5 meters. And that's the answer. So the answer should be A. Essentially, you can slowly fill up the water tank, and when you reach 5 meters, the force in the glue will become this limiting value of 2000. And if you pour even more water, then the glue is going to give, so the object is going to detach. So the maximum water depth or water height is 5 meters. And that's the end of the question.